Dear learners, welcome back to Ecological Economics again. As you know, this is part of our postgraduate diploma in sustainability science, and in the last few sessions we have talked about genesis of economic thoughts and ecology. As a student of sustainability science, how to understand economic thoughts in context to ecology. And we also learn about the environment economic linkages, right? So today in this session, the major focus will be on energy balance principles, right? As we know that an intimate connection has always existed between the human economy and natural environment, because nature provides the energy, materials, and ecosystem services that needed to sustain our life and expand economic output, right? So recently we learned that these resources and these ecosystem services, they are largely ignored by us in developing standard models of economic production. Consequently, resource events of the 1970s that confronted economies with an uncomfortable dilemma. Standard theories about how the economic process operated were unable to adequately explain some of the economic problems of the 1970s, which was influenced by the peaking of domestic oil production in 1970, as we call it as energy crisis. There is increased reliance on imported oil through 1978 and the energy-free shocks of 1973-74 and followed by 1980-81. As a result, all these models have been criticized for their lack of a sophisticated and realistic treatment of the role of natural resources and ecosystem services in human economic affairs, right? If you look into literature, you will find out that many of the critics have roots in a broad body of research known as biophysical economics. Biophysical economics begins with a conceptual model that sees the economy connected to and sustained by a flow of energy, materials, and ecosystem services. So here we are going to look on the evolution of biophysical model by looking at the formulation of the laws of thermodynamics in the early 19th century. So from these origins, the major focus of this session and another few more sessions will try to outline the development of biophysical theory to its current contribution to ecological economics. So up to this session, we will be able to explain influence of laws of thermodynamics and concept of entropy in economic thoughts in general, and we are also looking into thermodynamics and economic analysis in this session. If we look into laws of thermodynamics, as we know that if in the standard circular flow of economic model, the throughput is in physical units, and hence the physical laws must apply strictly to it. The economy, it constitutes of economic agents, the producers and the consumer, and the intermediary institutions between these two agents, that is between this producer and consumer, are the government and the market. On the other hand, the environment constitutes of the biosphere, the atmosphere, and the geosphere. So activities of economic agents and economic incentives arising out of exploitation of resources leads to environmental pollution and degradation of natural resources. So without the economy, most environmental issues are simply research question of concern to chemists or biologists without any policy significance. So the economy is heavily dependent on natural environment, as we know. The production sector extracts energy resources and raw materials from the environment. So the environment provides life supporting services to both sector of the economy, that is producer and consumer. So this effort environment also act as a that watering for the sectors. So we see here in this figure that shows the relationship. In this, the arrow shows the flow of the resources, or we can say or services from one sector to another sector. You will see here. You see in this the upper part of the figure represent the economy and the lower part represent the environment. And this upper part, the economy, can be divided into two sectors. One is production sector, another is consumption sector. The production sector extracts various factors of production from the natural environment as well as from the consumption sector and transform these two goods and services that are consumed by the consumption sector. So in this process of transformation, some waste is generated and it released into the environment. So some of the output they can also be reused within the production sector itself. So these arrows P1 and C1 show this recycling process within the sectors. So the level of extraction of energy and raw materials as well as the level of waste or pollution depends on the volume of production that in turn is decided by the consumption demand in the economy. So the production sector also depends on the environment for other environmental services. So consumption sector depends heavily on life supporting services of the environment. So some waste are also generated in the process of consumption. This effort, you will see here, human beings also enjoys various aesthetic and educational services of the environment. So environment act as a supplier of life supporting services, that means a source of energy and raw materials, and as a sink of receptors of waste product for production as well as the consumption sector. Thus, environment can be regarded as a special and composite asset that provides a variety of services, including the very basis of our existence on the planet Earth. So, the economic system, which we are going to discuss in this session, is a subsystem of the global ecosystem. The continued extraction of the economic subsystem from finite ecosystem constraints the availability of the resources for further use, thus limiting the size of the economy. This phenomenon can be discussed by using the laws of thermodynamics. And then what is thermodynamics? Thermodynamics is the study of the energy, the conversion of energy between various forms of and the ability of the energy to do work. Initially, you will find out three laws of thermodynamics that were posited. They were generated during the 19th century as the Industrial Revolution took hold and grew. Physicists came involved with the study of the flow of heat from machine as well as the chemical sciences that accompanied actual work. So, they were interested in gaining the maximum efficiency. In other words, we can say that they wanted to create a perpetual motion machine or one that could run off its own heat it created during the process of work, or so it could do more work and so on. So unfortunately, for the machine owners, the physicists failed to understand that. Basically, they saw that a perpetual motion machines were impossible. So in doing so, they came up with the three laws of thermodynamics. The first law of thermodynamics, second law of thermodynamics, and third law of thermodynamics. The first law of thermodynamics, you will see, basically says that energy or matter can neither be created nor destroyed. In terms of the machine, this means that the total energy output that is done by the machine is equal to the heat supplied. In other words, we can say that the change in that internal energy of a closed system is equal to the heat added to the system minus the work done by the system. Because the system operates in the real world and some energy always escapes into the outside world, that leading to both inefficiency. And the second law, it says that it is impossible to obtain a process where the unique effect is the subtraction of a positive heat from a reservoir and the production of a positive work. So energy exhibits entropy. It moves away from its sources. In this sense, energy or heat cannot flow from a colder body to a hotter body. One cannot keep a continual flow of heat to work without adding energy to the system. So in machine terms, one have to add energy to get more work, and the ratio of the heat to work will never equal to 100% due to energy expanding waste from its sources. Then what third law says? The third law explains that all processes cease as temperature approaches to absolute zero. This is the temperature at which molecules cease movement, cease producing kinetic energy. In other words, we can say that there is no energy. So from the first law of thermodynamics, what we know is that matter or energy can neither be created nor destroyed. It can change form, as in solid to liquid to gas to plasma and back again. But the amount of matter energy in the system, you can say in the universe, stays constant. In case of second law, what it states? It states that while the quantity of matter or energy remains the same, the quality deteriorates over time. Then how could this happen? Usable energy is used for productivity, growth and repair. So in the course of this process, that usable energy is converted into unusable energy, and usable energy is thus lost in the form of unusable energy. So entropy is used as a measure of unusable energy in a closed system. As it increases and usable energy decreases by the same amount, what first law says? Randomness increases. So energy retreats from its source, generally in the form of unusable energy. Let us take an example. Consider that's a fire. Now, when we add wood, means wood is what? It's matter. What is produces? Heat. Means we moves into the surrounding environment. Then smoke and water vapor, which again escapes into the surrounding environment, and eventually, is the last remaining of the heat is also added to the surrounding environment. So one is eventually left with cold, dead ash, which is taken on a random form, which is not seemingly related to the form of the wood. While the first law establishes the material balance, the second law highlights the impossibility of getting the usable energy, here wood, from the unusable energy, that is ash. So you will see here another illustration of laws of thermodynamics to the entropy hourglass. In this figure, in this entropy hourglass diagram you see here, the left one shows an isolated system wherein no sun enters and no sun leaves the system. And as per the first law of thermodynamics, neither sun is generated nor is it destroyed inside the hourglass. Sun in the top chamber has potential to fall and hence has useful energy embedded in it. Whereas the sun in the bottom chamber has no useful energy left in it to do work. Hence it is high entropy matter energy. Again, what suggested by the second law of thermodynamics, that is the entropy. Entropy is use-upness. That entropy increases in an isolated system. The right hand side hourglass shows a particular subsystem of the universe wherein the fossil fuels are consumed by the human beings to generate useful energy to do work. So unlike the universe hourglass, the right hand side hourglass depicts a closed system. Here also you will see the entropy increases, but in contrast to the left hand side hourglass, the human beings can alter the constricted middle of this hourglass and thus can alter the rate of change of entropy in the system. Then what is entropy? All the process of macroscopic changes are irreversible. That example includes, natural processes such as the growing and the blooming of the flowers, as well as technical processes such as the burning of fossil fuels in combustion engines. The entropy concept has been, coined in thermodynamics to capture this fact, what is happening in the nature. At the same time, this concept allows to make quantitative statement about the efficiency of energetic and material transformations. So the nature of the thermodynamic entropy concept can be understood from an analysis, the so-called Carnot cycle. What is that? An idealized model of a heat engine which performs mechanical work to the flow of heat from a hot reservoir at temperature. So here in this Carnot cycle, T is to a reservoir at lower temperature T1, right? The maximum efficiency of such a heat engine is 1 minus T1 by TH. The larger the temperature difference between the hot and the cold reservoir, the larger is the fraction of heat that can possibly be converted into the work. Clauses define a variable entropy S by ds equal to dq by t, where dq is the amount of heat transferred to or from the system in a reversible way at temperature T. And if you look into the word the entropy, it is based on the Greek word meaning transformation. So clauses prove the epochal result that entropy remains constant in any reversible cycle and increases during an irreversible cycle, right? So thermodynamic entropy is a measure of the ability or inability of a system energy to perform work. As the entropy of an isolated system increases, its available energy, also called as available work exergy, that available energy decreases. Here, that you will see in that entropy over glass, the sand in the upper chamber or left hand side has the potential to fall the place continuously. So, available energy corresponds to the useful part of energy which can be transformed into work. It does, combines the insights from both the first law of thermodynamics, also called as conservation of energy, and second law of thermodynamics means generation of entropy, right? So, available energy, what most people mean when they use the term energy carelessly. For example, when we said that energy used to carry out a certain process. So, the entropy law thus states that with every transformation, an isolated system loses part of its ability to perform useful mechanical work. So, as the system approaches thermodynamic equilibrium over time, its entropy will increase until it reaches a maximum value. So, in this final state of maximum entropy, the system potential for work is 0. And as far as the universe as a whole, that can be described as an isolated system. So, its final state is such a state of maximum entropy and zero potential for work, that is described as a heat death, right. Another scientist, Kenneth Boulding, probably was the first economist to highlight relevance of the law of thermodynamics to economics in his work in 1966, which was later popularized by Nicholas Gergiev-Rosen. So, what Boulding in his classic Economics of Coming Spaceship Earth discussed the transition from frontier economics to spaceship economics of the future. Thus, frontier economics in his analysis implies the economy of the past, where the growth in human welfare is associated with increased material consumption. So, Gergiev-Rosen pioneered the discourse on the critical linkages between thermodynamics and economics by elaborating the limits that the entropy law poses on the economic process. He considered it as the most economic of all physical laws. So, his work, Gergiev's work, is part of a long and rich history of using thermodynamic and ecological principles to study the economic system. So, his seminal work gave rise to a vast trend of fruitful research, but his postulates of the so-called fourth law of thermodynamics, which cannot be justified on thermodynamic ground, also initiated a heated and still ongoing debate in who is the economic relevance of the entropy law, or sometimes this means altogether. So, in thermodynamic view, the economy uses low entropy energy and matter from its surrounding nature environment to produce consumption goods, and discards every that's high entropy waste back into the environment. So, Gergiev-Rosen saw the entropy laws as a metaphor for the inevitable decline of such a kind of system, where every that act of production and consumption brings the economy closer to the doomsday in the form of hit that. Some of the recent chapter in history that bears testimony of this is what happened with that is the energy crisis of 1970s and economic disruption resulting from them, which made society acutely more aware about the connection between economic well-being and quality and availability of natural resources and ecosystem services. So this connection you will see can be looked into the ongoing debate on global climate change. We know that neither economy nor the planet at large is not an isolated system. If you look into the second law, it states that about an isolated system. So in isolated system, in thermodynamic equilibrium, only that is starts in the second law, right? So entropy is a meaningful and useful variable in open system near and far from equilibrium too. So any open system is subsystem of a larger and isolated system. So according to this second law, the entropy of the larger and isolated system has to increase over time, but the entropy of any open subsystem can of course decrease. So this is achieved by export of entropy from the subsystem to its surrounding through the process of energy in the matter. If we look into or views into open system and subsystems of large and isolated system, what it reveals? It reveals that an entropy decrease in an open subsystem necessarily has to be accompanied by an entropy increase in the system environment. That is the rest of the larger isolated system, such that the entropy of the total system increases. So, open subsystem can maintain an ordered state or even increase their order on the expense of the entropy of their surrounding increasing. Okay. So, if referring back to what the entropy of our glass, you will see in entropy of glass, the right hand side our glass representing an open subsystem of the fossil fuel consumption. This can in principle decrease its entropy despite running down the fossil fuel stock. So, this can be achieved through large scale import of useful energy from the universe surrounding the open system. So, while you will see the scientists like Zaskew Rosen's view that any economic action inevitably increases the Earth's entropy and brings it closer to its ultimate fate of a heat that may be considered too pessimistic. It is widely recognized that the ultimately limiting factor is the rate of low entropy energy influx from the sun. That is, you will see in the left hand side in our glass, and the rate of high entropy energy that energy export into the space. So let us start look into how Zaskew Rosen's view to economic system in thermodynamic economic analysis, right? As we know that Zaskew Rosen's work pointed towards the economic importance of the laws of conservation of mass and energy and the entropy law, So considering a conventional production function like Cobb-Douglas production function involving three inputs, that is capital, labor and natural resource. Here you will see in this Q equal to K alpha 1 and L alpha 1 into R alpha 2, where Q is the output per unit of time, K is the stock of the capital, L is the labor supply per unit time, and R is the flow of natural resource. From this, it can be inferred that with a constant labor of force L naught, one could obtain any given output. If the flow of natural resource satisfies the condition, that is R alpha or infinity 3 equal to Q naught by K infinity 1 into L infinity 2 or alpha. Consequently, we could maintain a constant output indefinitely with a diminishing amount of R if the quantity of K can be increased sufficiently. Of course, on an economic wide level, the increase in K implies an increase in the use of R. So that if K approaches infinity, R rapidly exhausted by the production of capital. Right. So other analyses have echoed about Zaskew's point that In certain application of interpretation that was widely used, models such as Cobb-Douglas or constant elasticity substitution production function, they embody the physically impossible assumption that a given output can be maintained as energy or material inputs that vanish if a manufactured capital can be increased sufficiently. However, if we look into the laws of conservation of mass and energy, they clearly dictate that no agent can create a state on which it operates. That is, manufactured capital cannot create a source it transforms and material it is made from. So, Rosen further added that the principle of entropy applied to material as well as energy. So, energy and the materials always are used together. We can never handle energy without a material receptors, material lever or material transmitters. So, thus, the Rosen's argued that there is a dual of the first law of thermodynamics, namely that no mechanical work can be performed without the use of some matter. It's also asserted by him that the second law of thermodynamics, which precludes the possibility of a machine converting energy to work with 100% efficiency, is due to imperfection in matter. So that is, there are no frictional materials, no perfect insulation, no perfect conductors, no perfect elastic material, etc. So this imperfection precludes the perfect conversion of energy into mechanical work. Consequently, a full understanding of material and energy transformation requires explicit attention to matter. The bottom line of Rosen is that due to material dissipation and generally declining quality of resource utilization, materials in the end may become more crucial than energy. So, Rosen also reject the infinite resources argument because they ignore the importance of change the quantity of that quality of matter. For example, if you look into the infinite resources argument, that's what he states that the literal notion of running out of material is ridiculous because the entire planet is composed of minerals. That's so there will be infinity. However, what Rosen exposed is that the fallacy of this argument by observing that by the same token one could argue that the planet will never run out of energy because the entire planet is full of energy. Indeed, if we look into the ocean, now the ocean contains enough energy to support undreamed of economic activity for millennia to come. However, the temperature gradient in the ocean is so small that for all practical purpose, the enormous store of energy is unavailable. In a similar vein, Rosen also argued that many of the materials are in low quality deposit that for all practical purpose render them unavailable. So, implications of material quality shares a common theme with the biophysical perspective, resource scarcity held by ecological economics and number of physical scientists. So, the biophysical manifestation of scarcity is the use of and oftentimes depletion of increasing amount of natural and human capital to deliver units of resource to society. So, a decline in the quality of natural resources based due to cumulative depletion and increase in the instantaneous rate of exploitation or an increase in the scale of extraction. Increase the amount of natural capital used to extract a unit. So, the biophysical perspective of scarcity measures the cost of obtaining natural resources in physical terms and thereby emphasizing the throughput of energy and material required to extract resources and the resultant impact of that throughput on a broad area of ecosystem services in different quantities and spatial scale. So, natural resources in a highly organized state are more economically useful because they have lower energy cost. The inverse relation between resource quality and the energy cost has been demonstrated when we use a wide range of minerals and fossil fuels. So, the fourth law, which is proposed by Rosen, with an argument that what assertion that intrinsically scarce material cannot be recovered from average rocks and the ocean is not correct. So, all elements can be extracted provided there is enough available energy. Thus, in theory, energy is the only resource that could ultimately limit economic growth. So, on a fundamental physical level, there is no such law as the fourth law of thermodynamics that was started by S C Khuman, whether at the molar level or molecular level. In principle, it is always possible to use the incoming high quality energy to trace, collect and reassemble the dissipated elements. So, some of the well documented counter examples to S C Khuman's fourth law include the biogeochemical cycles driven by the influx of solar radiation that constantly funnel dissipated material through a closed global ecosystem and temporarily generate high material concentration. Despite all these flaws in S C Khuman's definition of fourth law, his insistence on the importance of material for production and consumption process highlighted the difference between economic processes and natural processes. So, if we summarize what we have discussed in this session, is that we know that the physical economic foundation of ecological economy is provided with explicit focus on the laws of thermodynamics, where the first and second laws of thermodynamics, entropy concept and the characterization of abiotic and abiotic resources form an important part of the readings on ecological economics. Production and consumption activities are essentially the transformation of material energy that are governed by the laws of thermodynamics. So, there is always a close link between economic analysis and laws of thermodynamics. Thermodynamics is highly relevant at policy level as it provides an understanding of which processes do and do not have the potential to meet energy security and climate stability goals. With this,